Good day, everyone. Today, what we're going to do is we're going to start off on the next chapter, which is on solutions. Now, to fully grasp how solutions work, we need to first talk about what polarity is. Now, polarity happens in a chemical bond where the two atoms that are sharing electrons, or in the case of an ionic bond, transferring electrons, there is an imbalance in the two atoms' ability to pull electrons towards it. If you remember back in our first chapter, we talked about electronegativity. And electronegativity is essentially a measure of how much each atom wants or desires to acquire electrons from other atoms. Now, you guys know that nonmetals like to rip electrons off of metals. Because metals want to get rid of those electrons. So nonmetals usually have a very high electronegativity, close to 4, and metals usually have a very low electronegativity, close to 1. But that's the case for a lot of the ionic compounds and molecular compounds that we've talked about so far. But there's a whole sort of gradient of different electronegativities. For example, there are some metals that have a very high electronegativity for metals like gold, mercury, platinum, iridium, osmium. They all have electronegativities around 2, and that's very high for a metal. And there are some nonmetals that actually have very low electronegativities, such as carbon, hydrogen for sure, phosphorus, and sulfur to a certain degree that are, again, on the low end of 4 and closer to 2. Now, what we're going to do today is we're going to look at how to assess the polarity of bonds that are inside existing molecules, whether they be covalent compounds like my bromine here, where electrons are being shared, or ionic compounds like sodium fluoride over here, where electrons are going to be transferred from the sodium to the fluoride. There is a way to assess the polarity of these bonds, and you'll be happy to know that it's right on the top of your periodic table, right in the center, where it says predicting bond types from delta En values. I'm going to pop it up on the video there for us to look at while we go through these questions. What we're going to do is we're going to take a look at 6 molecules, determine the delta En, or the change in electronegativity, difference in electronegativity, if you want to call it that as well. That is going to determine what type of bond happens between two atoms based on is one atom going to give electrons away, or are they going to share electrons, but those electrons are going to be closer to one atom than the other because one atom wants to pull electrons more? Or is there not going to be any polarity because the two atoms have a equally strong pull on electrons? I'm just going to fix things up here. The first thing we're going to look at is the bromine diatomic molecule, which is Br2. And bromine is one of the halogens that form a diatomic when it's in its natural state. So two bromines will just bond together because they both would prefer to have a stable octet. And it's a great way to do it. Let's just share a couple electrons, and now we both got 2. We're both happy. So to calculate the change in electronegativity of a bond, what you have to do is look for the electronegativity of the two atoms that we are trying to examine and subtract one from the other. Generally, you want to subtract the larger number from the smaller one, but since these are 2 bromine atoms, they're going to have the same electronegativity, which is 2.8, which gives us a delta En of nothing. Now, if you look at your periodic table on the top, the section about polarity of molecules is split into 2 parts. You have the top part, which is for metal to non-metal bonding, and then the bottom part is for non-metal to non-metal bonding. Now, bromine is not a metal and it's bonded to not a metal, so we're going to examine the bottom half of the table, and 0 falls in the range of 0 to 0.4 there, which means this is a non-polar covalent bond. Now, what this means is that yes, it's a covalent bond, so the electrons are being shared, but because the bromines both pull the electrons with the exact same force, it's non-polar, which essentially means that the electrons exist in a state essentially exactly in between the 2 bromines. This bromine's pulling them towards it, this bromine's pulling them towards it this way. Think about it like a tug of war, and they're both equal sides, so the electrons end up sticking right in the center. For the next one we're going to look at is sodium fluoride. Now, you guys will probably recognize this as an ionic salt. We've talked definitely about sodium chloride before, and fluorine is even a higher electron polar than chlorine. So you'll notice I don't have a diagram for this because I know that this is a metal and a non-metal bonding together. So I got to figure out what type of bond I'm going to have before I draw the Lewis diagram for it. So let's calculate the delta En to start. Okay, fluorine is the most electronegative element on the periodic table with an electronegativity of 4.0. It's excellent at pulling electrons. If you look at sodium, its electronegativity is only 1.0, so that leaves us with a 3.0 delta En. Now, if we look at the table again, at the top there, we are going to be examining the part for metal to non-metal. Sodium's metal, fluorine is not. And you'll see that indicates that it falls in the ionic range, which if you look at the chart there, stops at 3.2. So this is one of the most ionic bonds that two atoms can actually have together. Now, what does this mean about the actual structure of this? Well, because it's an ionic bond, that means that electrons are being transferred. So the Lewis diagram for this is a sodium cation and a fluorine anion with 8 electrons in its outer shell. When a bond is ionic, it means that electrons get ripped from one to another. So the electron, this is about as far away as the electrons can be from sodium. They dislike sodium so much that they left sodium to go to fluorine, right? So that's ionic bond is essentially a super polar bond. If you want to think about this in terms of tug of war, the fluorine has already won the game of tug of war against sodium. Sodium's already given up, gone home, relinquished his trophy or his electron to fluorine, and fluorine's doing his victory dance as we speak. So extremely high difference in electronegativity causes electrons to get ripped from one atom to another, which you guys already know from earlier. All right, the next two atoms we're going to look at are carbon monoxide and gold 1 iodide. Now, carbon monoxide, again, I've given you a Lewis structure for it because we know this is a covalent compound because it is a nonmetal bonded to a nonmetal, and they always create covalent compounds. Now, you'll notice that there's a lot going on in this molecule. For example, there's a triple bond in between the carbon and the oxygen. Carbon's got a lone pair of electrons over here to give it its 8 in its octet. Same thing with oxygen here. Important to note that the fact this is a triple bond doesn't actually change anything about how we calculate the change in electronegativity. We're still just comparing one atom to another. So if I'm going to calculate the change in electronegativity here, we're going to use the electronegativity of oxygen, which happens to be very high at 3.5. And we're going to subtract the electronegativity of carbon, which is 2.5. And that's going to give us overall a change in electronegativity of 1.0. Examining the top of your periodic table there, you'll notice that since these are both nonmetals, we're going to look at the bottom section, and that falls within the range of polar covalent. So a polar covalent bond just means that electrons are being shared, but those electrons are much closer to one of the atoms than the other. The oxygen is much stronger at pulling electrons than the carbon. So what this means is the electrons here are going to spend most of their time, all 6 of them, because there's, a lot of electrons being shared, are going to spend most of their time much closer to oxygen than they are to the carbon. Now, there is a way to show this. I have it in the lesson. When you have a polar covalent bond like this, you do so using what's a Greek symbol called delta. And so for this, because the electrons are closer to the oxygen, it gives the oxygen kind of a fake negative charge. It's not a full negative charge like fluorine up here because it stole the electron completely from sodium. No, it's like a part negative charge. It's just enough to offset the balance in this molecule so that the electrons are closer to the oxygen. In the same regard, the carbon ends up with what's called a delta plus, or a faint or partial positive charge, because the electrons are further away from it, and therefore that gives it a sort of positive-ish charge. Once you put those two deltas on there, then you draw an arrow between them going from the positive end to the negative end, and that shows the polarity inside that molecule. Again, because electrons are being shared, there's no ions here. It's just a partial charge, a kind of charge, a negative-ish and positive-ish charge, if you will. And again, going back to our example of the tug of war, oxygen is much stronger than carbon, so it is pulling the electrons closer to itself and away from the carbon atom. All right, on to the next one. We have gold 1 iodide. Again, because this is a metal and a non-metal, I haven't drawn the structure. Let's figure out what the delta En is first, because that's going to tell us what kind of molecule we have here. All right, so delta En here. Now, iodine has a electronegativity of 2.5. And gold, if you remember earlier, I said that's one of the most electronegative metals on the periodic table. And it has an electronegativity of 1.9. Now when you subtract those two guys, you get 0.6. Then we're going to look at the top of our periodic table. We're going to look at the top part because that's for metal to non-metal. And 0.6 falls in the range of polar covalent, which means gold and iodine actually transfer electrons in a very similar way to carbon and oxygen. Even though this is a metal and a non-metal, it's polar covalent. And covalent means sharing of electrons. So iodine doesn't have enough electron pulling power to rip the electron off of gold. So instead they decide to share it. Now that being said, the electrons are still going to end up being much closer to the iodine because iodine again has more electron pulling power. And again, we can draw our delta plus and delta minus in our molecule because it is a polar molecule. You can't put those onto non-polar molecules or ionic molecules, but you certainly can onto polar ones. And that gives us our diagram of gold 1 iodide. And I realize I forgot to put the lone electrons or the non-bonded electrons on there. And we're all good. Awesome. Now we got 2 more to do. The next one we're going to do is, just the most important molecule probably on planet Earth, water. Now we're going to do an entire lesson on water. I've already posted it to the OneDrive, so you can check it out if you want. But we're going to go into a lot more detail with it next week because water's polarity is what gives it its amazing property to be able to, dissolve lots of different things, create acids and bases. The polarity of water is quite important. Now, the reason why water has any polarity at all is because the non-bonded electrons that are stuck on the oxygen repel the electrons that are shared between the oxygens and the hydrogens. So they end up pushing them down, and it's kind of like a V shape instead of a straight across shape like one might expect. Now, the only bond here is between oxygen and hydrogen, so we can calculate the change in electronegativity. Oxygen's 3.5 and hydrogen's 2.1. And that gives me a change in electronegativity of 1.4. There we go. Which, if we look at our table there, indicates that we have a polar covalent bond. But there's 2 of these bonds in this molecule. So essentially, we have a big delta minus here at the top, but you have a delta plus at the hydrogens for both of them, and you can draw an arrow between both of them, like so. Now what this does is this creates an area of fairly negative-ish charge up at the top near the oxygen and 2 areas of fairly positive-ish charge down near the hydrogens. As you guys know, this unit is called solutions, and polarity is what's going to help us understand why dissolving happens, why some things dissolve and other things don't. The last example there is iridium 3 phosphide. So that's 1 iridium atom, one phosphorus atom. All right, again, this is a metal and a non-metal, so I'm going to leave drawing my molecule when I'm done. Phosphorus is the non-metal there. It has an electronegativity of 2.1. And then iridium has an electronegativity of 1.9. Now, that gives us a delta En of 0.2, which is extremely low. It's a metal and a non-metal, so we're going to look at the top of the table there, and we're going to find that this is a non-polar covalent bond. So again, it's going to share the electrons. We're going to draw a line, but because this is so close to zero, iridium and phosphorus basically pull the electrons towards each other in, you know, I just realized there should be 3 lines there because it's sharing 3 electrons, right? 3 electrons shared to a phosphorus that wants to get 3 electrons. I apologize for that. So we can't actually draw any of these deltas and stuff on this molecule because there is no imbalance in where the electrons are. Yeah, that is 0.2 and that is technically larger than 0, but anything that close to 0 is on an atomic scale essentially negligible. And we end up with a nonpolar covalent compound. This will definitely not dissolve in water. Ionic compounds dissolve in water by dissociating, by coming apart. Again, there's no reason for this molecule to come apart because the electrons don't have any particular preference to go towards the phosphorus or the iridium. So it's not going to dissociate when it comes in contact with water. It's not going to dissolve at all. All right, the next lesson coming up, we're going to look at molecular polarity. So check that out. Talk to you soon.